So the topic is simple linear regression equation model using OLS. As we already have studied in the earlier tutorial, that the standard form of simple linear regression model is the equation which is yi is equals to beta naught plus beta 1 xi plus ui. We already studied in detail what these variables are. Like yi here is the dependent variable, xi is the independent variable, beta 1 is the slope parameter, beta naught is the intercept, and u is the disturbance term that includes all which has been excluded in the model. Therefore, the true relationship between any two variables x and y, in fact capital X and capital Y, is the same equation, the basic equation, whereas the estimated regression line will have another equation that will be represented as yi hat, and we'll put the hat on these variables to show that it is the estimated one. So the same becomes yi hat is equals to beta naught hat plus beta 1 hat xi. We'll put the basic equation which was yi is equal to beta naught plus beta 1 xi plus ui as equation number 1, and we'll put the estimated regression line equation as equation number 2. Therefore, the estimated relationship would become yi is equals to beta naught hat plus beta 1 hat xi plus ei, which will be equation number 3. This is we are doing to replace the values further. Now here in this equation, this ei is the estimate of the true value of the random term. Now there is a diagram that we're going to look into to understand it further. Here is the diagram. You can pause the video and look at it carefully. Here you can see that the true relation between x and y, which was our equation number 1, is being shown, and the estimated regression line based on it is also drawn here, which is being shown in the diagram, as well as the estimated relationship with the help of E1, which is nothing else but the estimate of the true value of the random term capital U, which was in equation number 1. Now here we can see the estimation line, but here ei is different from ui, which was in equation number 1. So the ei of estimated line is different from ui of the basic equation. Now how it is? So here I have listed out a few points which makes ei different from ui. You can even pause the tape and can watch it further carefully. See, ei is the residual or the deviation of the dependent variable from its fitted value yi hat. Now this ei arises from the estimation process, whereas ui is associated with the true regression error of the original basic equation line. Now this ei can be either positive or negative, or can even be 0. Now if they are squared and added, assuming that they have non-zero values, it will be positive and will vary directly with the spread of the points from the line. Also, different values of beta naught hat and beta 1 hat will give different lines, and hence a different sum of the square residuals will also happen. So now the working of the model starts. See, from point number 2 that we have written already, which says that ei is the difference between the observed value of yi and its estimated value yi hat. So we'll do the same, we'll take the difference. So that way we can write that ei is the difference between the two, yi minus yi hat. Now if we put the value of yi hat from equation number 2 that we worked out earlier, you can go back and see. In this equation, then what happens? Ei becomes equal to yi minus, putting the value of yi hat, which is beta naught hat minus beta 1 hat xi. Now what the principle of least square says, it says that we aim to choose that combination of beta naught hat and beta 1 hat which minimizes the summation of this residual error term, the square of the residual actually that minimizes it. So what is this sigma EI square? It is the sum of the squared residuals, as we know that EI is the residual. Now how we do that? We'll square these deviation and we'll take their sum. So you can just go through this entire working has been given further. I have simply just derivated it further. You can watch it carefully, peacefully, and if there is a doubt you can simply put it in the comment. See, further I have taken the sum squared and then I have taken the partial derivatives that we'll do further. So now what we have done here, we have taken the summation and have squared them on both sides of the equation. The equation which was EI is equals to yi minus yi hat. So I have taken summation, that is sigma, with the limits I is equal to 1 till n, and have squared them. Here again you can see in equation 3.1, that becomes our equation 3.1, where we have extended this equation of left hand side a bit, where we have simply put in the value of yi hat inside the brackets. So it becomes sigma EI square equals to sigma bracket opens yi minus beta naught hat minus beta 1 hat xi bracket closes whole square. So this becomes our equation number 3.1. Now we have the purpose of finding the sum of beta naught hat plus beta 1 hat that minimize their sum. For that we'll differentiate the sum of the squares of residual with respect to beta naught hat and beta 1 hat, and we'll equate the partial derivatives equal to 0. We'll put the value equal to 0. So this has been done here. We have taken the partial derivative as per the first order condition for the minimization. We have taken the partial derivative first with respect to beta naught hash. We have simply partially derivated equation number 3.1 here, and we have put in it equal to 0. Here you can see in the working. So we have finally got sigma under bracket yi minus beta naught hat minus beta 1 hat xi equals to 0. We'll further derivate it to get the value of sigma yi. We'll take it on the other side, and this gives us equation number 2, where sigma yi is equals to n beta naught hat plus beta 1 hat sigma xi after the whole partial derivative thing happens. And now we will take the partial derivative of the same equation, that is 3.1, with respect to beta 1 hat of the same sigma EI square. Now after taking the partial derivative of equation number 3.1 with respect to beta 1 hat, now putting the entire equation equal to 0 as per the condition, we have got our equation number 5, where it comes out to be sigma yi xi equals to beta naught hat sigma xi plus beta 1 hat sigma xi square. Now from equation number 4 that we worked out earlier, where we got the value of sigma yi, we'll put it here. It will process it a little, where we had sigma yi is equals to n beta naught hat plus beta 1 hat sigma xi. We'll take out the value of n beta naught hat here. So with the help of this equation, with little further processing, we got the value of beta naught hat, which is equal to sigma yi upon n minus beta 1 hat sigma xi upon n. So here we already know that this ratio sigma yi upon n is known as this ratio shows the mean value. So it is equals to y bar, and similarly this sigma xi upon n shows the mean value of x, which is x bar. So we can put it as beta naught hat, which is equal to y bar minus beta 1 hat x bar. That becomes our equation number 6. Now we'll put the value of beta naught hat in equation number 5. We'll simply put it, and you can see the working here. I have worked out and derivated it further, putting the values, and finally what we reached at was the value of beta 1 hat, which is equals to sigma xi yi minus y bar sigma xi upon sigma I square minus x bar sigma xi, which can further be a little process to get sigma xi yi minus n y bar x bar upon sigma xi square minus n x bar square. That becomes our equation number 7. So here if we put the value of x minus x bar, that is difference from the mean, we can put it as small xi, and similarly for y. So ultimately beta 1 hat becomes sigma xi yi upon sigma xi square, all in small. This shows that the above formula are expressed in terms of the original sample observation x and y. It can be shown that the estimate beta 1 hat may be obtained by the following formula, which is expressed in deviation of the variable form, their means. Thank you. Hope it could help.